Hello, everyone. Sorry, I'm just checking that the laser is working. So just really quickly carry on from yesterday. I've been castigated for overrunning yesterday, so I will try to stick to the time today. If you let me know when I get to 10 minutes, I will try to stop. The answer to the question yesterday got it Mike Turner. I think other people got the answer, which is each one of the 10 passengers goes to one floor. That's how we get the maximum H and the maximum S, if you want to explain it in that way. And then in between the maximum value and the minimum value, you have a 10 billion, maybe less than 10 billion, but you have a large number of combinations in between. That's why the value of the round trip time is variable. So this is a difficult subject, chaos. Has anyone heard of chaos before? Okay. It's different from randomness. That's a serious comment. So a random system is what we saw yesterday, with people getting in, 10 passengers getting in, and each one of them deciding, we can't predict, there's no way I can predict where this person is going. It's in his or her mind. But chaotic systems are different. So chaotic systems appear to be random, they're not actually random. The best example of a chaotic system, anyone knows? One of the best examples of a chaotic system which we live with every day in the British Isles, yes, the weather system. That is an excellent example of a chaotic system. So what I'll try to do in the first part of this presentation is just try to explain to you what a chaotic system is. In the second part, I will explain to you what Dr. Albadri has done, what he was trying to achieve. So there was a guy called Edward Lawrence, 1961 at the MIT. He was developing a very simple model for weather. He had built 12 equations to predict the weather, pressure, temperature, wind speed, and so on. And he wanted to be able to predict what will happen next. So first, he wanted to make sure that his model predicted correctly what was happening in real life. He had a printout, and then he would type in some numbers about the temperature and the pressure and so on. But what he noticed is that his model was quickly going out of sync with what was happening in reality. Now, at the beginning, he was doing very well. Very, very good. So his model was working very, very well. But you can see as time went by, the deviation got bigger and bigger, and then it just became a completely different system. And that's not to do with randomness. His model was good. He had developed an excellent model. But what was happening in here is that the system was very, very, very sensitive to initial conditions. And that is what a chaotic system is. A chaotic system is very, very sensitive, extremely sensitive to initial conditions. This is what happened. The number that he picked from the printout was 0.506. And he typed that number, 0.506, into the computer. But in fact, the real number was to 6 decimal places, 0.506127. He ignored the 127, and he thought the 127 would not make any difference. And in most linear systems we deal with today, let's say I was the rope. Where's the gentleman with the rope? Very kind. He gave me the. If you were looking at the rope and how the rope would extend, if you made a small error in putting the input, you will get a very small error in the output. That's a linear system. But a chaotic system, eventually, the system got completely out. And this is a new breed of systems called chaotic systems, weather systems, and there are things like, for example, predator-prey populations. If you have a fox and rabbits in a forest, for example, that is a very chaotic system. And so what he did then, he went back, corrected the 0.127, and he started getting better results. Other systems mentioned here by Dr. Ali. Dr. Ali works for London Underground in the mechanical engineering department. There are some colleagues of his here. And what he was trying to do, let me go to this slide so you can see clearly. Okay, what's this? We have SASE. Is SASE here? Yes, they would recognize this. What is it? Gearbox. What do we use a gearbox for? For? Yeah. More specifically, we use a gearbox to drop the speed and raise the torque. except in one location. Does anyone know where that location is? Where we do the opposite? Wind turbines. So what Dr. Albadri did, he picked 5 locations on the gearbox. I'm not sure if you can see the... Anyway, 5 different locations. He measured the temperature precisely as a time series on these 5 locations. What he also did was he switched off the escalator for some time so that it cooled off, and then he switched it back on again. So he has a region 1 and a region 2. Are we okay for time? Now then he took this data, and each one of those signals he plotted it on what we call a phase plane. And let me show you what this is. What a phase plane. You probably haven't seen it before, or has anyone seen a phase plane before? It's quite a what we do. We take the signal and we take a delayed version of the signal, or we take the signal and its derivative, and we plot it. So you have an x-axis, a y-axis, and then time. So as time goes by, you plot this. And these curves, what they're giving Dr. Albadri, they're giving him different, the 2 regions. You remember the 2 regions which we had, heating up and cooling down. So this one here and this one here. So he was seeing that there's actually a difference in behavior or in the phase planes in both cases. So region 1 is the one at the top for output shaft, non-driven shaft, input shaft, end gearbox, and front gearbox. For the 5 locations, he was getting these different shapes, and they were different for region 1 and region 2. What this starts telling you is this a chaotic system or is it not a chaotic system? And then there's another more complicated plot, which is a Poincare plot. Henry Poincare, anyone heard of him? He's a polymath. What's a polymath? Does anyone know? Polymath. Someone who's like Isaac Newton. He's done all sorts of things and so on. So, and this becomes even more complicated, and from it, you can then start coming up with a model. This is the simplest I can explain it. Making it any simpler would require much more time. But this is actually trying to model the chaotic behavior of a system using a Poincare map. So, does everyone understand what a chaotic system is? Yeah?
Like the weather.
Like the weather, yeah, that's a good, and it's highly dependent on initial conditions, yeah. Thank you very much.